Hello, welcome back. So, in this lecture we would like to understand the significance of computational analysis in assessing the wear behavior. So, you might know that leading edges of supersonic aircrafts experience high temperature, particularly at the nose edges or tailing edges, and the temperature may rise around 800 Celsius as per the simulation studies. So, this temperature rise is because of the intense aerodynamic heating along with the stagnation pressure. So, you know these supersonic aircrafts, they travel at a very high speed of Mach 2 or Mach 3 at altitudes of around 10 to 20 kilometers, and while traveling they may also experience erosion due to impingement of particulates, those from the atmosphere, and then these particle impingement may lead to the material damage. So, most of the conventional materials, they would fail under these thermomechanical loads. So, that necessitates the use of ceramics, and the ceramics for this particular use, that they have high melting points, so that you can use safely at these temperatures of 800,000 Celsius without any degradation in the strength. Those ceramics are generally called ultra high temperature ceramics. So, ultra high temperature ceramics are preferred for these components used for the supersonic aircraft. So, in the family of the ultra high temperature ceramics, zirconium diboride based ceramics are attractive because of their important properties. For example, very high melting point of more than 3200 Celsius and high thermal conductivity of around 60 watt per meter per Celsius, very high hardness. So, that may lead to superior wear resistance, Young's modulus very high around 500 gigapascal, and good conductivity and moderate density. This moderate density is helpful for using this material for structural applications. And so, excellent chemical and physical stability in various atmospheres, those are candidate materials for high temperature applications. And it is already drafted in several reports that by adding certain amount of silicon carbide in zirconium diboride, we can improve the oxidation resistance of these ceramics, and also we can improve the strength of this ceramic. So, for example, without having silicon carbide, the zirconium diboride will have around 300 to 500 MPa strength. By adding silicon carbide, the strength may go even up to 1000 MPa. So, but most of the reported studies on the erosion wear behavior of ceramic composites, various ceramic composites, not only zirconium diboride, various ceramic composites, they were focused on the experimental work, and the results of this experimental work were subsequently used to estimate the performance in simulated environment. And simulation studies, those simulated environments were selected to which are close to the flight conditions. That means, experimental work is done, the results of the experimental erosion work will be taken as a input for the computational studies or the simulation studies close to the flight conditions. Now, in the present study, we demonstrate a combination of the experimental one and computational work is more useful to understand the behavior of these ceramic composites in high temperature erosion conditions. Particularly, we will see how this computational analysis will be helpful to understand the erosion behavior on erosion behavior of zirconium diboride silicon carbide based composites. Particularly, we will see the significance of computational analysis in understanding the experimental erosion test results on thermo-erosive stability of zirconium diboride silicon carbide based composites. So, the objectives of the present study are to study the erosion behavior of zirconium diboride silicon carbide and titanium composites using a solid particle erosion tester at high temperatures of 800 Celsius, and to understand the dominant wear mechanisms in the selected erosion conditions, and mainly to determine the temperature and stress distribution in the eroded region using finite element analysis, and to understand finally the thermo-erosive structural stability of the selected zirconium diboride silicon carbide titanium composites. So, these composites were prepared by spark plasma sintering. First, the powders of the zirconium diboride silicon carbide and titanium were taken and mixed in a proportion of zirconium diboride with 18 weight percent of silicon carbide with titanium amount varying from 0 to 10 weight percent. So, these powder mixtures were kept in a die and then subjected to spark plasma sintering. So, spark plasma sintering gave a decent density of more than 98% density. So, we can see the spark plasma sintering result, the shrinkage versus time. In this particular experiment, the spark plasma sintering was done in a 3-stage process. This is called multi-stage spark plasma sintering. So, based on the previous understanding, so multi-stage spark plasma sintering was conducted. So, we can see at 1400 there was a holding of 5 minutes, and then at 1500 there was a holding of 5 minutes, and finally 1600 there was a holding of 5 minutes. So, this is shrinkage versus time curve for different composites are shown. Now, in general we can see there are 3 stages of the shrinkage increase corresponding to sintering stages. So, first in general the rate of the shrinkage is lower in first stage and a bit higher in the second stage, and aggressively increase the very aggressive shrinkage rate is aggressive in the third stage. With respect to composition, now you can see when the titanium was used, so we can see shrinkage was higher in particularly first and second stages. So, this helps us. So, this indicates the addition of titanium in the composite powder mixture of zirconium diboride and silicon carbide will improve the densification or will densify the material at lower stages of sintering itself. So, the shrinkage further increased to the next stage, and then maximum shrinkage was obtained in the third stage of sintering. The microstructure of these composites particularly show zirconium diboride grains and silicon carbide particles, right, silicon carbide particles, and then titanium. So, the titanium being a lower melting material, so it forms a liquid melt while increasing the temperature during sintering. So, this liquid melt penetrates between the particles of the zirconium diboride and silicon carbide and facilitates sintering. So, such a liquid phase sintering gives us a densification earlier than that used without this titanium. So, this zirconium diboride silicon carbide or particles, zirconium diboride grains and the silicon carbide particles are distributed, and then we can see the EDS analysis of these particular phases. This A phase, this is zirconium diboride, that is you can see significantly the zirconium, so and boron, so zirconium diboride, and you can see this black phase or dark phase which is rich with the silicon. So, this silicon carbide and silicon carbide, and we can see the zirconium and silicon both are present along with the titanium in the matrix, and we can also see certain contamination from the ball milling medium. So, ball milling was done mainly to mix these powders of zirconium diboride, silicon carbide and titanium. So, but the ball milling was done by using balls of tungsten carbide. So, tungsten carbide came into the powder mixture. So, it still remains. So, you have a contamination even after the sintering. So, zirconium diboride grains and silicon carbide particles. So, in this matrix of zirconium diboride grains and silicon carbide particles, we have certain zirconium, silicon, titanium rich phase at different locations. So, these two materials of zirconium diboride with 18% silicon carbide and zirconium diboride with 18% silicon carbide and 10% silicon carbide were taken for investigating the erosion wear behavior. So, these are designated as ZS T0, ZS T10. ZS T0 means no titanium, T10 means 10% titanium. The hardness and the fracture toughness values were determined by Vickers indentation. So, you can see the hardness increased from 17.5 gigapascal to around 29.2 gigapascal by adding 10% titanium in the baseline composition of zirconium diboride silicon carbide. And fracture toughness also improved from 3.7 to 9.0 MPa root meter. So, you see there is very large improvement in the hardness and fracture toughness by adding only smaller amount of 10% titanium in the composite. So, it also indicates the densification is improved by adding a titanium that reflects in the microstructural characteristics and then the mechanical properties. So, in another study it was also found that the grain size of the zirconium diboride or particle size of silicon carbide are almost similar to that what we started as a initial powder particles. So, there is no much difference in the size of average particle size of silicon carbide or average grain size of the zirconium diboride. So, this also indicates the spark plasma sintering conditions were sufficient to prepare a material of high density with good mechanical properties. Among the two investigated composites, the composite with the titanium showed higher hardness and fracture toughness. Among the investigated composites, the composite with the titanium addition showed higher fracture toughness and higher hardness. So, with this information, so we conducted the high temperature erosion test. So, high temperature erosion test was done using a high temperature particle erosion tester. So, silicon carbide particles which we call erodents of around 40 to 50 micron meter size, particle size were mixed with air, and then this mixture were used to erode the surface of the composite. So, we can see the real time photograph of this material when it was at a high temperature of around 800 Celsius. So, we see the kinetic energy per unit area for the leading edge of the hypersonic vehicle flying at Mach 10 speed at 30 kilometers altitude. So, the kinetic energy can be estimated if you know the flight time and the cross sectional area of the exposed leading edge and this mass flow rate of this impinging erodent particle, where this m dot can be found out by density, area, cross sectional area of the leading edge, the particle flow rate, mass flow rate of the particles, and C a constant, generally max C is a maximum of annual dust concentration, which was taken at 129.6 micron gram per kilogram of the air. So, this was taken from the literature. Okay. Based on the above calculations, the kinetic energy deposition is estimated in for the hypersonic vehicle leading edge is around 35.6 megajoules per meter square. So, the kinetic energy we know this by half m dot v square T of exposure. So, we know the mass flow rate of the impinging particle, the time of exposure in the test, and then we know the density of this erodent, the sample cross sectional area. The erosion experiments were conducted with the deposited energy of around 50.5 megajoules per meter square, very high, higher, more than 130% than what we have as a kinetic energy deposited. So, just for the safe side, and we took for the conditions which give us the kinetic energy deposition of around 50.5 megajoules per meter square. So, we selected the parameters accordingly and the particle size velocity and the time of testing was 1200 seconds and the erosion was done at 90 degrees impact angle. So, we get around 50.5 megajoules per meter square. So, the sample surface was exposed to equivalent heat deposition as given here, and the force equivalent of momentum lost by erodent per unit time were also calculated. So, but erosion experiments were done at 1073 Kelvin, that is 800 Celsius, and normal impact. So, this selection of these 1073 K is also based on the limitation of the erosion test equipment. A normal impact was selected because we know the ceramic composites, they usually fracture to a larger extent at 90 degrees angle and then that lead to maximum wear. So, we selected these two, temperature and the angle. So, now we can see the X-ray diffraction analysis for understanding the phase evolution in high temperature erosion. So, we see here this ZS T0 means before erosion, just is after sintering, and ZS T0 EJT means erosion tested. Similarly, ZS T10 before erosion and ZS T10 after erosion. Now, you see the phases of before erosion are just zirconium diboride, silicon carbide and zirconium oxide, right, for the sample without having the titanium. When titanium was added in the powder mixture and sintering was done, so the sintering reactions, or that means before erosion, we have certain sintering reactions, zirconium diboride with silicon carbide with titanium, that gives zirconium carbide, titanium diboride, and also zirconium silicide and titanium boride, titanium carbide, titanium silicide, zirconium oxide. So, several possible reactions can be thought. So, after erosion we still have few new phases formed on the surface. zirconium diboride, silicon carbides, right. And then along with this we also have zirconium carbide, boron oxide, silicon oxide, and then titanium silicide or zirconium silicate. So, there are certain new phases formed because of the high temperature erosion. So, let us understand such phase analysis by considering the thermodynamics and the kinetics. So, after sintering the erosion was done, and these are the probable reactions, because we are seeing all these reaction products. So, these reaction products are thought to be because of these reactions, right. So, let us understand the feasibility of such reaction mechanisms by thermodynamics or kinetics. So, Gibbs free energy versus temperature was plotted for these reactions, and we can see the formation of this zirconium carbide. We can see here the formation of this zirconium carbide, boron oxide or silicon oxide, right. So, we can see it is feasible within this temperature range of around this 500 to 1273 Kelvin. Within this range, these are largely negative. That means, it is highly possible reaction forming a zirconium oxide. So, similarly zirconium oxide and zirconium carbide. So, silicon oxide is usually formed on the silicon carbide surfaces and the high temperature. So, we still have this thermodynamically, this is feasible, whereas the formation of titanium silicide and zirconium silicate, titanium silicide and zirconium silicate are also possible generally at more than 1000 Kelvin, but these are still nearer to the 0 value of this Gibbs free energy. So, we can say that these are still feasible, right. And the equilibrium constant was also plotted as a function of time. You can see all reactions have the equilibrium constant positive, that indicating the feasibility of such reactions. And of course, with the titanium silicide and zirconium silicate formation is generally possible at more than 1000 Kelvin, right. So, these reaction mechanisms are possible, and this fact is supported by the thermodynamic and kinetic feasibility as well, right. So, all these reactions are possible in the high temperature conditions used for the erosion. So, we have certain zirconium carbide, boron oxide, silicon oxide, boron carbide, zirconium oxide, silicon oxide, titanium silicide, zirconium silicate, etc. So, we have several phases on the surface, right. One important observation is there is no titanium here. So, even before starting the erosion, just sintering itself resulted into certain compounds of titanium boride, titanium silicide, titanium carbide. So, we do not have any metallic titanium. So, that indicates that the titanium was consumed completely during sintering and then formed different phases, right. Because of the formation of these hard phases, so we have an improvement in the hardness and fracture toughness. So, let us understand the mechanisms of the material removal in the given erosion conditions. So, you see this zirconium diboride silicon carbide, there is lot of chipping, right, there is a lot of chipping, and then the cracking. EDS analysis also indicates the oxidation. So, when the titanium was added, we can still see the chipping and cracking, even the surface become more rough, right, more rough. That means, it indicates more cracking, more cracks, right. So, more cracking and chipping and the oxidation, so are also are observed in the eroded material of zirconium diboride, silicon carbide and titanium. So, overall the material is removed by cracking, chipping and oxidation for these two composite materials. The results from the high temperature erosion indicate, so the high temperature erosion test, the material removed is measured by weight loss and converted into volume loss and then converted into volume loss per kilogram of erodent, that we call erosion rate. So, the high temperature erosion test results show that there is a decrease in the erosion rate from ZST 0 to ZST 10. You can see from 35.86 mm cube per kilogram to 33.49 mm cube per kilogram change in erosion rate observed when we add 10% of titanium in the composition. And if you relate this erosion rate with the mechanical properties, we can see there is a large improvement in the hardness and fracture toughness, almost 1.7 times increase in the hardness and 2.5 times increase in the fracture toughness by adding 10% of titanium in the baseline zirconium diboride silicon carbide composite. But this combination of increased mechanical properties resulted only 6% or 6.6% improvement in the erosion wear resistance. So, there was a large improvement in the mechanical properties by adding 10% titanium in zirconium diboride silicon carbide composite, but this reflected in only 6.6% improvement in the wear resistance. This is very interesting. So, now this is where we need computation analysis to understand such a behavior. So, for this finite element modeling was carried out, right, using ANSYS software. So, you can see the CAD model, high quality structured grid with second order elements for a better accuracy was generated to discretize the solid domain. We can see the CAD model here, this is the sample, right, and then we can see the highly refined mesh near the erosion crater. So, this can be explained by the 3-dimensional 20 node coupled field solid elements. So, these sigma indicates the principal stresses on each element. So, all the properties like thermal conductivity. So, in the FE modeling, the boundary conditions used are the surface of the sample is exposed to equivalent heat deposition and a uniform force equivalent of momentum lost by the erodent per unit time on the exposed portion of flat face of the composite. And other boundary condition is modeling. In modeling, we considered the conduction as the heat transfer mode at the interface of this zirconium diboride silicon carbide sample, filler and sample holder. So, we have this filler is used to fix the sample inside this metal holder, sample holder. The interface is present along the circumference and back wall of the zirconium diboride silicon carbide sample. So, we know this, we have the displacement constraints even at the back wall, right, and along these walls of the holder. The displacement of rear face of the sample holder is constrained in all the directions, right. So, stress and the temperature distribution was studied first by transient thermal analysis and then thermostructural analysis. First, initially transient thermal analysis was performed to estimate the temperature distribution in the sample. then the nodal temperature distribution obtained from the transient thermal analysis was mapped to the structural domain, and then we have a coupled thermostructural analysis by solving appropriate equations. So, first the results from the transient thermal analysis. So, we can see this is a sample of ZS T0, it is sample of ZS 10, this is ZS T10, this is ZS T0. Now, you see the temperature distribution here. For the ZS T0, the temperature interval you can see here from around 840 to 841 in the vicinity of this crater region, right. Whereas, for the ZS T10, in the vicinity of the crater region, the temperature interval is between 855 to 862. So, a thermal gradient of approximately 300 Kelvin per meter in case of ZS T0 and 4500 Kelvin per meter in case of ZS T10 were observed. So, high temperatures are also observed in the filler material, and mainly because of its lower thermal conductivity compared to these two samples, either ZS T0 or ZS T10. Compared to these two sample materials, the thermal conductivity or the filler material is very low. So, the conduction is difficult in the region of this filler. So, you get a high temperatures at the filler regions. This can also be due to lower specific heat capacity of the filler compared to these two materials. So, we can also see the displacement analysis. So, the this is again, this is for the ZS T0, it is ZS T10, right. So, maximum displacement of around 0.38 mm near the sample circumference for the ZS T0 and 0.40 for nearer 0.40 mm nearer the sample circumference of ZS T10 are found, right. You can see this is in meters. So, but only a small reduction in the displacement field is recorded as we move radially towards the center. But if you see the stress analysis, so von Mises stress values were calculated. So, in case of ZS T0, there is a less difference in stress from the center of this crater to the crater periphery, right, to the crater periphery. So, the stresses are around 38.6 MPa in the center of the crater to 49 MPa for the crater periphery. You can see here 49 here, this is 10 power 7. So, it is 38 to 49 MPa if you move from the center of the crater to the crater periphery. So, this less difference in the stresses from the crater center to the crater periphery for ZS T0 is because of the less difference in the temperature in the crater region. So, almost uniform temperature is maintained. So, you do not have any difference in the stresses. But if you see the ZS T10, large difference in stress from the crater center to the crater periphery. So, this is mainly because of the distinct thermal gradient visible in the temperature contours. So, you can see there is a large difference in the temperature contours, and you can see this the center of the crater is again nodded. So, you can see for ZS T10 the temperature at the crater center is higher than the temperature near the crater periphery. So, the stresses found were also very large in case of ZS 10. So, maximum stress of 282, you can see the maximum stress of 282 MPa is found at the crater center, and this stress falls to 192 MPa nearer the crater periphery, right, in case of this ZS T10. So, such a difference in the stresses can be understood because of the temperature differences from the center of the crater to the periphery of the crater. So, for this ZS T10, the temperature at the center is higher than the temperature at the crater periphery, right. You can see this crater, this is simulation for the temperature contours, this is the temperature contours for the crater region only. So, we must understand there are certain inherent stresses generated. So, there are certain inherent residual stresses at room temperature because of the difference in coefficient of thermal expansion of various phases present in the material, but these stresses tend to relax at higher temperature. So, the stresses in the oxidized sample as estimated in this work using this finite element analysis are additional stresses developed during high temperature erosion. So, we can also see there is very less weight loss because of this erosion. So, this very less weight loss indicates the ability of this zirconium diboride silicon based multi-phase ceramics to retain the properties in the stress conditions in the high temperature erosion, right. Let us also understand the effect of oxidation on the mass loss in erosion. Very carefully the samples were flattened to see the oxidation layer thickness. So, this is ZsT10, the maximum thickness of this oxide layer is around 25 micron meter, whereas for ZsT10 the maximum thickness is around 7 micron meter. You can see the ratio of mass gain due to oxidation to the mass loss due to erosion is very less, right. So, 0.0035 for the ZsT10 and ZsT0 0.0124. So, that means very negligible effect of the oxidation on the mass loss due to erosion. So, the mass gain due to oxidation is negligible when you compare with the mass loss due to erosion. That means, we can say the material is removed by the mass loss during erosion significantly. So, we can also understand that the additional presence of the refractory compounds, for example, titanium carbide, titanium silicide, these contribute in improving the hardness or toughness for the zirconium diboride silicon carbide titanium composite. So, it leads to improved stability. Finally, let us conclude the salient results obtained from this study. The erosion rate of zirconium diboride silicon carbide titanium composite is 6.6% lower than that of zirconium diboride silicon carbide composite. This is also 18. The eroded samples reveals mainly the cracking, the chip formation and oxidation as dominant mechanisms of material removal for the composites. X-ray diffraction analysis as well as the realistic assessment of the thermodynamic stability at the computationally predicted wall temperatures indicates the possibility of the formation of several phases: zirconium carbide, zirconium oxide, boron oxide, silicon oxide or titanium oxide on the composite surfaces in the selected conditions of erosion. One order of magnitude higher stresses are determined from the thermostructural analysis. So, these higher stresses are attributed to the reduced effect of better mechanical properties like hardness and fracture toughness and the erosion loss for zirconium diboride silicon carbide titanium composite. So, in spite of having large improvement in the hardness and fracture toughness, there was less improvement in the erosion wear resistance for the zirconium diboride silicon carbide titanium composite compared to zirconium diboride silicon carbide. So, this discrepancy can be understood only by this computational analysis that we did using finite element model. So, the understanding obtained from this approach of combining experimental results and a computational analysis is very much significant in selecting suitable material for the thermal protection system of the supersonic vehicles experiencing the erosion wear. So, this particular study proposes or demonstrates necessary guidelines for assessing thermal, erosive, structural stability of materials utilizing a novel approach of coupling experimental results and computational analysis. So, I hope you like this part of this lecture. Thank you.